So good morning, my name is Tania Misus. I work for Enagas. Enagas is the main gas infrastructure operator in Spain. I'm also chairing the Methane Emissions Group in Gas Infrastructure Europe, and deeply involved in several methane emissions projects and initiatives. I will be moderating the next session. I have 8 excellent panelists with me, and they will be presenting their projects on methods and methodologies to quantify methane emissions. And in the previous session, so you have seen that we are living a momentum on the methane emissions topic. On one hand, the governments are setting targets, so they have committed to reduce methane emissions by 30% in 2030. Also, an important number of companies have joined on voluntary basis OGMP 2.0 and committed to report their methane emissions according to the most accurate methodologies, which includes both the top-down and the bottom-up approaches, as it was presented by Anke. And then also the European Commission is at the moment developing a legislation covering methane emissions in the energy sector. We are also living a revolution from the technology point of view. So there appear almost everyday technologies to detect and quantify methane emissions. And this is good to ensure that the industry is reporting their methane emissions in the most accurate way, and also ensuring that they are including all the methane emissions in their methane emissions mitigation strategy. So Nigel Yarrow is a research scientist at the National Physics Laboratory. He will present the results of the study on reconciliation of the bottom-up quantification and the dial measurements at an LNG site. So Nigel, thank you.
Hi everyone, these are my slides, so that's a good start. Next Tanya, as I said, I'm Nigel Yarrow, work at the... Oh, sorry. Can everyone hear? Okay. I'll just wait for... Is everyone here? Is that good? Okay. Yes, so scientists at the National Physical Laboratory. I'm going to talk a bit about reconciliation between component and site level methane emission measurements, but also more generally about methods and measurements. Okay, so just a quick introduction, what we're going to cover. A little look at some of the reporting guidelines we have for methane emission reporting, what we mean by reconciliation and why we're trying to do it, some techniques and methods we have available to us, and the differences when we're talking about these two terms, what we mean by techniques and methods. I look at some data, and then I talk about some challenges we faced when trying to reconcile data sets, and then wrap up with conclusions and some of the future work NPL are going to be working on. So what do we have by way of methane emission reporting guidelines? Broadly speaking, there's these sort of two categories, the IPCC's tiers, and then OGMP2, their levels. They're not sort of really cross-comparable, but generally as you go up the tiers or levels, the requirements get more stringent, with most companies maybe reporting around level 2 or 3 of the OGMP scale, with the goal to be everyone up to level 5, where actual measurements are required both at the source and site level. So reconciliation, we're trying to take one data set and make it consistent with another data set, specifically for OGMP level 5. We're trying to reconcile estimates of site emissions made with source level measurements with site level quantification. And the aim here is to provide confidence in these estimates. So we're validating them against these total site level quantification measurements. A couple of things here that's important to note that this reconciliation of this type is a check of data at the time and not necessarily of the annualized emissions. So taking a snapshot quantification measurement at the site level, and we're going to check that data against what the estimate would be at that time, not necessarily the annualized emissions. And that these measurements should be made independently of each other. We shouldn't have reliance on component level estimates for the site level and vice versa. So let's take a step back and talk about the techniques and methods. And here I think it's important to go into sort of how we make measurements, the features of a measurement. So we've got sensors, the most sort of fundamental being a part of a measurement, something that responds in the presence of a target. Many sensors available. The next sort of level down, we've got the technique. This is like the application of the sensor into an instrument, maybe combined with some other things like some other optics, other sensors, more than one sensor. And again, many techniques available: optical gas imaging, LiDAR, sniffing, some examples. They may employ the same sensors, they may be different. And then we move on to like the deployment media, so the mode by which this is put into the field. It could be fixed on a pole, could be on a vehicle, could be a drone. And then the combination of all these features is the methodology. And the methodology then also includes how we make the measurement. So a protocol, other measurements that are needed. For example, if you need some wind measurements to get a flux, any quality control procedures that are in place, all of these things are the methodology. And so you could have the same sensor approach and deployment media, but done in a different way, and we've got a different methodology. And so there's a requirement for these methodologies to be standardized, so that everyone's doing them in the same way and to ensure performance, and then to be validated to be proven to give sort of accurate results. And this is where it's important to say that it's the methodology that is validated and not any one of these features of the measurement. So we're not validating the sensor, or we're not validating the technique, we're validating the whole method, including how and other things that go into that. And we don't have a lot of published standardized methods available to us. We have Method 21, US standard for component level detection, but it doesn't include any quantification in that method. EN 15446, and again a similar detection level method with some emission factors included to estimate quantification, and a recently published standard, EN 1768, which is a validated method for total emissions to atmosphere. This is some of the techniques and methods that NPL have at our disposal and regularly deploy. So on the left, the component level sniffing and OGI, so for component level detection, and some quantification at that scale with a high flow sampler. This is a thing that NPL has its own method, but no sort of independently validated method is available for that technique. And then on the right hand side, we've got our differential absorption LiDAR, a remote sensing site level technique for quantifying total emissions to atmosphere. So these two plots show some data that we've collected across 2 sites, and these are measurements of the functional element level scale. So that could be a compressor, a vaporizer, those kind of things, or something on a unit on a site. And we're looking at, in the grey, quantified emissions using a remote sensing dial technique. And then in blue, which admittedly for the most part you can't see, is quantified emissions of the same, the aggregate quantified emissions for the same functional elements made at the component level using high flow. And we can see that there's dramatically lower emissions are measured using the high flow. And this sort of could be likely that the highest emitting sources are out of scope for these component level surveys, which raises challenges when we're trying to reconcile these two data sets. And this could be a good thing. This could be because leak detection and repair programs are working, so we find the leaks, we repair them, and what's left are these emissions that are out of scope. So moving on, this is another presenting data in another way. So this plot shows site emissions broken down into different areas of the site, but in the blue and the orange we have estimates of site emissions from a component level survey with a mix of specific and generic emission factors. And then in the grey, again, site emission measurements from a remote sensing technique. And again, we can see a discrepancy between what we're estimating and what we're measuring. Some would say that we've got similar emissions from 2 different component level campaigns about 5 years apart. This could be because maybe the leaks reappear after so many years, maybe they're not permanent, or maybe because if a subsample of leaks is statistically relevant, then we see the same sort of emission profile. A couple of other things we can point out from this sort of data. The fact that we've got some granularity in the data, we can see that we may be able to direct our approach for detection and quantification surveys maybe differently. So instead of just surveying everything and repairing, we can focus our repair surveys where we know there's high quantification. The other thing to point out is this potentially the issue of what we call non-continuous sources, so something that varies considerably with time or duration or magnitude. And if your site level technique can't distinguish these, we may be skewing the data. So we've got two totals here, one with excluding these non-continuous and one including. And we can see that if a site level technique has included them but doesn't know about it, we could be sort of not comparing the right systems. And the final column at the end, at this point in time, we saw there was a large emission on site, very large but relatively short-lived. But if a single site measurement technique had included that in its site level measurement, we're sort of dramatically skewing our data. And so this is a challenge when it comes to reconciling these two data sets. So what are some of the challenges? We talked about maybe potentially having incomplete data. So our component level survey may not be capturing the majority of sites emissions, at least in magnitude. And this could be because they're potentially out of scope for those surveys. And we may not be using the most appropriate emission factors. So if we're just using general emission factors from literature, they might not be the most appropriate to apply in these cases. So the more specific we can get emission factors, maybe this gap will close. And so this issue of non-continuous sources, methods may be or may not be able to detect them and separate them. So this complicates our attempts for this reconciliation and for annualizing snapshot measurements, and has the effect of potentially skewing the data. And this is where we need sort of close cooperation between site operators and measurement providers to understand what's happening on site, where there are these types of emissions happening, and how their measurement will take that into account. Is it affected? How is it affected by these types of measurement? And then I want to touch on uncertainty. This is something that's potentially often overlooked when we talk about measurement, but it is really important. And if we don't know the uncertainty of both data sets, we can never really know how successful we've been in our reconciliation attempts. So this is a really important thing. And this is where standardized and validated methods will help. If we have a standardized way, everyone's doing it the same way, then the uncertainty will sort of almost fall into place, I think. So just to sum up, we have these high standards or ambitions even for methane emission reporting, commendably so, and we need to do that with this sort of requirement for these two categories of measurements at the site and source level. Many techniques for detecting and increasing number to quantify, but a few methods we talked about. Actually, there's only relatively few methods which have been validated. And there's a need for these standardized validated methods to ensure performance and to have confidence in our results. We looked at some data and showed that there's sort of these large discrepancies observed between the two source level measurements and site level measurements, and also the estimates that are based on some of these measurements and the site level measurements again. And there are significant challenges to overcome when we're trying to reconcile these data sets. So that could be because of sources that are out of scope for some methods, maybe not using the most appropriate emission factors. This issue of non-continuous sources, so how are we going to take these into account? Do we need to have methods that can separate them, or maybe we just, as long as we know about them, maybe that's enough? And then this assessment of the uncertainty, really important that we have uncertainty on both sides, both data sets. And I just wanted to touch on this idea that the methods may be validated for a particular scope, and they may not have the same scope, but they're complementary. So detection and then quantification methods are complementary in our goal, which is ultimately to reduce emissions and to know how much we reduce them by. So what are some of the things that NPL will be working on in the future, focusing on this reconciliation, and to understand some of the challenges that we're trying to overcome them, and including reconciling data from more and different techniques. Developing new methods and validating these methods for high-frequency measurements and long-term monitoring as just some of them. And then developing these standardized methods, so performance standards, and then methods to validate other techniques, so like a method to validate validation, I guess. And then going on to this taxonomy, so we need to know what we want from our measurement, what we're capable of achieving, and where the gaps are, and hope that then we can try and fill some of those gaps, but we need to know what they are first. Okay, thank you. Any questions?
So, in principle, the idea is to have all the questions at the end of this session, unless you need any clarification now or any burning question. If not, so I propose to move to the next speaker. Yeah. Okay. The next speaker now will be Stefan Schwietzke. He's senior scientist at the Environmental Defense Fund and it's advisory also in the International Methane Emissions Observatory, and he will be presenting a project on reconciliation of the bottom-up approach and the drone-based measurements in a gas offshore platform. So Stefan, thank you.
Can you hear me? Can you hear me? No? Hello? Oh. Can you hear me? Oh, great. Thank you. So this is a little bit like air travel experience. First I get denied boarding and then I get upgraded to a headset. I see it coming. It looks good. That's me. It looks familiar. So, hello everyone. I'd like to start with acknowledging the colleagues that I did this very collaborative project with. And they are from Scientific Aviation, CCOPS, FlyLogix, University of Michigan, Neptune Energy, and Texo. And I will talk about how we can use drone-based monitoring systems in an offshore environment. And so why the offshore sector? It's currently understudied, even though about a third of global oil and gas production is coming right from there. It's different from onshore in several ways. Access and logistics to do those measurements are usually more difficult. Boundary layer dynamics can be difficult, especially with relatively cold surfaces. The operations at those rigs are usually quite complex. The different types of them that need to be differentiated. The platforms, one example which you see here, sometimes they're interconnected, so it's not just one platform by itself. There are additional methane sources, like for example, transport of oil through tankers, which need to be loaded and unloaded. They also tend to be highly productive, and they're often manned. And I would like to start giving some context by highlighting this study by Amy Foltz, which was just published last year, and which was able to really empirically verify reported emissions offshore. And what was very special here is that it was the first study that was really comprehensive and did repeat measurements in an offshore environment, and it demonstrated how much temporal variability there is offshore. And so you see this with the different sites that were measured here. And at each site, the measured values could be dramatically different from one time to another. And those were most likely related to the operating conditions. And so we'll get back to this topic in a minute. What this study, which Amy Foltz published, was all about is quantifying emissions at a regional level, giving sort of a big picture what happens representatively in one region. What this study is about is to help establish the science for more accurate company reporting, and that company reporting happens at the facility level. One framework that we mentioned here already is the Oil and Gas Methane Partnership 2.0, on which companies reporting that produce about half of global oil and gas. And direct measurements are needed to achieve the gold standard at the source and site level. In order to do those kinds of measurements, the operators need to ask themselves several questions, including which monitoring technology to use, which measurement strategies, what are the strengths and limitations of each technology and strategy, what is a representative sample, And is there anything from the learnings over the past decade from the onshore that are transferable to offshore? And so to address some of these, we did this joint R&D project, which included the oil and gas industry, represented here by Neptune Energy, which operated this facility. It's called Cygnus Alpha in the North Sea. Monitoring tech providers, and an NGO, which happened to be EDF. And in this study, we really wanted to compare source-level operator reporting and then measurements at the facility and sub-facility level. And so for the sub-facility, we did rotor drone measurements, which I'll explain a little bit more, but we basically did a lot of these downwind transects stacked on top of each other for different parts of the facility. And we also did fixed-wing drone measurements, which would circle the facility at different levels. And so in method 1, so the facility level emissions quantification, there's a photo from underneath the wing of the FlyLogic Seacops fixed-wing drone, circling here this facility. And it would do so at very tight intervals, actually, of about 5 meters vertically. This is the drone. And then in the method 2, which would do the sub-facility level emissions quantification, this was operated actually from over here, from the heli deck. This is what you see on this picture, where the drone was just starting. And then it would fly downwind of the facility. In this case, the wind was coming here from the south towards the north. Then we also had an infrared camera looking at, in this case, combustion sources, which come up simply as a warm source, where we could actually see some of the combustion sources and make sure that the drone is actually in the plume, just really for directing it. And the upper part is for a compressor, and the lower example is for a flare. And so the known emission sources from this facility really informed the flight strategies of the rotor drone. And so this included, for example, knowing where the compressors are, gas turbine generator, so different types of exhausts. We knew where the vents were here, there were vents here, a flare tip over here, and then fugitives obviously could occur everywhere. This here was the wellhead, this was the production platform, and this is the accommodation platform. And so the first flights of the rotor drone were really downwind transects of the whole facility. We noticed pretty quickly that doesn't work so well because you have about 10 to 15 minutes of drone flight, and this is about 100 meters or so from one end to the other, and so you really don't do a lot of transects. And then for the other flights, we then broke it up to the different jackets. In this jacket, we even did individual parts in there. And here are some illustrations of the data that we would get this, in this case, from the fixed-wing drone. So, which will show you the methane concentrations of these concentric circles stacked on top of each other. And then in the next step, once you work with the data, you interpolate this to a grid, and then you start seeing where the highest enhancements are on the downwind side of that facility. And then for the rotor drone, here's also an illustration. Where here on the production platform, we did some measurements here over at the flare, so you see the enhancements there. So at a much higher level of resolution, obviously, than what you see from the fixed-wing drone. And the same thing at the lower part where the known vents were. Okay, and now we're getting to some preliminary results here where we did this cross-comparison. There's a lot of stuff on here, but I want to put your attention to a few things. So the first interesting insight was that the flare, so we're comparing the inventory with the rotor drone and the fixed-wing drone. We saw that in the inventory, the flare was the biggest emission source, which we could confirm with the rotor drone. Then another insight was, if that moves forward, was that it was quite puzzling that the top-down results from the two drones didn't quite match up. There was a factor of 3 or more between them. And then the other important thing to realize is that those drone flights happened on different days. And so now for this reconciliation, we need to ask ourselves what was happening here. Was there real temporal variability? As we saw in this Norway example, so between the different flights, doing flights on 2 different days here and 2 different days here? Or was the rotor drone estimate low biased, or was the fixed wing drone high biased? And so there starts the reconciliation process. 2 examples of this are shown here, where we're basically trying to see did we really capture the plumes right in the different on the different drone flights. And so here, for example, you see this video where the drone goes here back and forth invisible, and then here in infrared. And you can compare here with the data at different altitudes. Does it match certain sources? Okay, my thumb is going numb. Okay, here we have it. Sorry. Another example for this reconciliation process is to look at the operational status of the facility in a lot of detail. So, for example, we got here from the operator, from Neptune Energy, the throughput from the 2 different compressors on the different days. What does it look like? So this is second-level data where we can try to analyze when exactly did the 2 different drones fly, and could the differences in operation explain some of the differences. So this is what we're doing right now in the observed emissions. So some preliminary conclusions from this work. In terms of logistics, we demonstrated that the offshore on-site methane measurements are possible, also via external contractors. So this is really important to do these routinely in the future, to do the company reporting. There is a trade-off between measurement detail, which the rotor drone develops, and the ease of application, which comes with a fixed-wing drone. In terms of scientific and reporting insights, the reconciliation through OGMP, it requires both source level and site level information, measurements. And the different empirical methods not only help acquire that, but they're also quite complementary, as you could see, having like different levels of detail. But it also means as soon as you apply different methods, you will see how robust your results are, right? You have just one method, you might be happy with the result. You get another one, you will see where the full range of estimates really lies. In terms of the homework that we still have to do is look more into this plume characterization, different frequencies and densities of measurements that were used with the different drones. Flux estimation, look more at uncertainty characterization for the specific conditions during the flights. And as I just mentioned, sort of the rig operations, how much of the observed variability in emissions could be due to variability in operations. In the big scheme of things, I think this was still or is already a promising result, because even though we have this puzzling discrepancy between the rotor and fixed wing, you'll see that we were already able for this specific facility to say the range is probably somewhere in here in green, right? And what we know is from other measurements, the range of emission levels at the facility level could be much larger, right? So we're pretty sure that this facility is not anywhere up here. It's also not zero. It's somewhere in here. And this is where the empirical data helps already, knowing much more than just from an inventory. And so thank you for your attention and happy to answer questions later. Okay.
Okay. Okay, so our next speaker is Jean-Daniel Paris. So she's a research scientist at the Laboratory of Science of Climate and Environment in Paris. And he will be presenting the GERG project on top-down technology. So he will be presenting the benchmarking that was performed last year.
Thank you very much. No. Also not this one, no. So there is no file? No? Can we do another change in the in the order of speakers, maybe?
So, Jacob, so maybe you can join us. So there is some issues with the presentation of Jean-Daniel. So Jacob Shaw is a research associate at the University of Manchester. He will be presenting a project on methane emissions and flaring efficiencies in the North Sea. So Jacob, welcome. The floor is yours.
Yeah, those are mine. Is this working? Yeah, can you hear me? Yep. Okay, excellent. Hello. Thank you, Stefan, for trying to present this earlier. You are on there, you are at the bottom, so you probably could have done a good enough job about it. It is Amy's work. So yeah, hi everyone, I'm Jacob. I'm a postdoc at the University of Manchester, and I'm going to be talking about our measurements of methane emissions and flaring efficiencies from the oil and gas sector in the North Sea. So it's not just me that's done this work. There's a whole bunch of people, many of whom are probably in this room as well. So thanks must go to all of those. Am I doing this right? Yes, there we go. Okay, so just a bit of a brief overview of what I'm going to be talking to you about for the next sort of 15 minutes. I'll start off with a very quick introduction to the oil and gas sector and methane emissions. I'm then going to talk in maybe a bit more detail than Stefan did about Amy's paper that was recently published in Atmospheric Chemistry and Physics. So that will be the bulk of this talk. I'll talk you through the flight campaigns, the data that Amy used, and then come on to the mass balance method, which Anka very nicely introduced earlier for us as well. And then show some results and comparisons that Amy drew from that as well. And then the second part of this presentation will be on more recent work, which uses data from another flight campaign in the North Sea, where we're looking at flaring efficiencies and some emission ratios. And that's all very preliminary. So by way of a brief introduction then, globally, methane emissions from the oil and gas sector are responsible for about 80 teragrams of methane a year. If you sum up all of the man-made methane sources, it comes out to roughly a fifth for the oil and gas sector. And if you sum up all methane sources, so include natural methane as well, then the oil and gas sector is responsible for about a tenth of all methane. Emissions from the oil and gas sector primarily come from three main areas: intentional venting, leakage, and of course flaring as well. So the offshore oil and gas, there have been very few studies done on that. I've got a slightly different number to Stefan. I'm not sure why, even though about 20% of production is done offshore, although Stefan said a third, but that just makes my point even more. And then very few studies have also been done on flaring emissions, even onshore. So there have been some recent studies of offshore, done in a couple of production regions. The Gulf of Mexico is one, and then also the North Sea. So just to summarize a few of the recent conclusions from that. Stuart Riddick led a shipborne campaign measuring emissions from, I think, about 8 facilities. His methane flux was about 7 grams of methane per second. And then Shona Wild, who works at the University of York and was involved in the AOG campaign, which I'll come on to talk about later, got a number that was quite a bit larger, 120 grams of methane per second, but with a large range on that. Then James France, who is in the audience and will be speaking later, reported on a carbon-13 isotopic ratio for the methane from oil and gas in the North Sea, and that's minus 53 per mil. And that's very useful for source identification. And in a similar way, the ethane to methane ratio can be used for that as well, and Shona reported on that too. So in terms of our own campaign, or the data that Amy used for her paper, there were 2 that we used. The first of those is the Moya Arctic campaign. Moya was a project, a global project. It was called Methane Observations and Yearly Assessments. And it was primarily looking at emissions from natural sources such as wetlands. It went all over the world to Senegal, Uganda, Bolivia, Finland. And we basically got a bit of extra funding to do an offshoot from that and look at some emissions from oil and gas in the Norwegian sector of the North Sea. The Moya campaign used the UK's FAM research aircraft, which you can basically think of as a large flying laboratory. The second campaign was Scientific Aviation, which we heard a little bit about from Stefan. They're a research company which specialize in measuring fluxes, and they used a smaller aircraft, which you can see pictured there. It's a Mooney propeller aircraft. So in terms of what these aircraft are capable of measuring, the FAM aircraft can do quite a lot. You've got a lot of room for instruments. Methane itself was measured with an LGR fast greenhouse gas analyzer. That was initially operating at 1 hertz, but was upgraded in 2019 to operate at 10 hertz. Moya Arctic involved 3 flights in 2019. The Scientific Aviation is obviously using a smaller plane. It can measure various trace gases. Methane in this case was measured with a Picara analyzer, and they did 10 flights, slightly later in the year, but a similar sort of time frame. So both campaigns used the same method to quantify the emission fluxes. So I used the mass balance box method, which Anka did talk about earlier. That basically involves an upwind flight leg to ascertain the background methane mole fraction, and then building up, I don't know how you use the pointer, a vertical plane downwind of your methane source and integrating over that to calculate an emission. What the Scientific Aviation guys do is a slightly different variation of this, where they use a volume of a cylinder rather than a box. And that's based on Gauss's theorem, and you can read more about that in Steve Conley's paper. So coming on to the results then, Stefan did show this. So Amy measured results from 21 facilities, and you can see those across there. The emissions were attributed to specific rigs and platforms based on a Lagrangian transport model called FlexPart. The emissions that Amy calculated range between about 0.1 gram to 40 grams of methane per second, with a mean of about 7 grams of methane per second, which actually agrees really quite closely with Stuart Riddick's results. If you want to scale that up to annual numbers for comparison to operator reports or inventories, I think that's about 2 to 1,200 tons per year, and with a mean of about 200 tons. Stefan mentioned some of these sort of uncertainty error bars that we've got there. They largely came from the mixing heights, uncertainty in that. So basically, we were unable to always fly as low as possible to see the bottom of the plume, and sometimes fly to the top of the plume as well. So in some cases, that was unconstrained, and we had to make some assumptions on how vertically high the plumes were. As various other people have mentioned in talks, these are snapshot measurements. So when you do scale up to an annual estimate, you're very dependent on what was going on the rig at that time. So what Amy's tried to do here is break down the emission results based on what operators reported they were doing. So she's categorized that as primary and other operations, and you can read more about that in her paper. What Amy also did was compare with the operator reported emissions, that's shown on the right plot there, and she found very good agreement generally with those. I think they actually turned out to be a little bit higher, 15% higher or something than the measurements. Amy then also looked at a global inventory, this global fuel exploitation inventory, which was published by Scarpelli et al. But she found much poorer agreement with that. I think that was about 50% lower on aggregate. And she attributed this to two sort of primary reasons. One, the inventory was slightly out of date. I think it was for 3 or 4 years before our study. And two, to the way in which the inventory was compiled and how the emissions were aggregated over grid cells. Okay, so now on to the sort of the second part of this. I realize I've not got a great deal of time left, so I'll try and be quick. So flaring is widely used to dispose of natural gas in cases where it's not used for sale. It involves the combustion of hydrocarbons and the fuel gas to form carbon dioxide. And this results in the emissions of various components such as carbon monoxide, nitrogen oxides, sulfur dioxide, and any sort of components of the unburnt fuel. So the International Energy Agency reported that 142 billion cubic meters of natural gas were flared in 2020. But despite this, there seems to have been very few studies done on emissions from operational flares. There's quite a few from test flares, but they're not always operating under operational conditions. The few that do exist seem to have been done in the Bakken Shale formation in the US. And we should note that emission inventories use an assumption of 98% efficiency, and I guess these studies are quite close to that. So the flight campaign data that we used for this, we used Moyer Arctic, which I've already mentioned, and also the assessing atmospheric emissions from the oil and gas industry, this AAOG, which did fly a little bit earlier in 2018 and a bit of 2019 as well. But both of these use the FAM aircraft. Through both of those campaigns, we managed to identify about 58 flare plumes, or 58 plumes that we think are due to flaring. They were found by concurrent emissions in methane, ethane, carbon dioxide, and nitrogen oxides. And this plot just shows some of the flight paths over the North Sea. So one of the measures that you can use for flaring is this combustion efficiency, which is essentially a measure of the carbon in the flare gas versus carbon in the fuel gas. So Nara et al. Published an equation for doing that, where you essentially look at the enhancement in carbon dioxide against the enhancement in carbon dioxide plus the enhancement of methane. Now, I guess that assumes that the fuel gas is 100% methane, and we know that's probably unlikely to be the case. And since we had continuous measurements of ethane on board the FAM aircraft, we've modified their equation to include the ethane component of that as well. So this plot over on the right shows a histogram distribution of combustion efficiencies calculated with and without sort of accounting for the ethane, and then we've just got them plotted against each other there with quite a nice linear correlation. I guess currently this is all very preliminary work. The current sort of takeaway here is that the Moya campaign, the combustion efficiencies measured there, were quite a bit larger, or approaching 100%, when compared with those measured in AOG. And we're currently attributing that to the fact that Moya flew over the Norwegian sector, whereas AOG was all in the UK. But open to anyone else who, if they have a different conclusion from that. The other thing we can look at, because the FAM aircraft also measures NOx, is the NOx emission ratios. So this is essentially the ratio in the enhancement of NOx versus the enhancement of some reference gas. And we've used CO2 as a reference gas here in purple, and methane as a reference gas here in green. You can see in both cases there we've got a skewed distribution, quite a large range. So these are deviating from the median ratios quite significantly, especially for methane here. We think this might indicate something about the flare operation. We're not entirely sure at this point. It probably requires a bit of thought. If anyone has any ideas about this, do let me know. What we can say at this point, though, is that, again, the Norwegian sort of sector, the Moya flights, typically seem to show lower amounts of NOx, even though they had higher combustion efficiencies. Okay, so just to quickly conclude then, we've measured methane emissions from 21 facilities in the Norwegian sector of the North Sea, and that was using the mass balance method. The operator reports appear to be in good agreement, and I guess that's kind of indicating best practice here. The inventory that we looked at, this Scarpelli Global Fuel Exploitation inventory, underestimated emissions, primarily for possibly two reasons. Firstly, that it's out of date, and secondly, the way in which it aggregates emissions. We should stress, though, that there's always a need for these regular and independent surveys to monitor emissions. And then finally, we started to look at combustion efficiency, destruction removal efficiency, which I've not had time to show, and NOx and ethane ratios for 58 flare plumes. And our current sort of conclusion that we can draw from that is the inventory assumption of 98% seems fairly reasonable, although there is a bit of a long-tailed distribution, which might affect things. I don't have any. I did have a slide of references, but that must have been in a newer version. Yeah, that's all. Thank you very much. Happy to take any questions. Should I just leave this here? Or? Yes, I think so. Oh, okay, yeah. Second time.
Okay, so, no. Hello? Is it working now? No.
This one is working, yeah?
Maybe your settings. Hello? But, okay. You were already introduced.
Okay, so after a few more adventures, I will present you the result of a study on site-level quantification of methane emissions. It's actually there is no author or co-author indicated on the first page because the list is quite long. It's a very collaborative effort with several of the groups that are present in this conference today. So actually the role that we had at LSCE was to synthesize on the give, let's say, an independent view on the measurement that were provided to us. So we participated upstream of the study, and downstream we were on the field, and we tried to have, let's say, an impartial vision of things here. The reason for this study was that there is a need for more first-hand information on what is available on the shelf in terms of measuring methane emission, quantifying fugitive emissions at the site scale. So it's the study emanates from the GERG, so it's a French acronym actually. In English, it's a group for European Group for Gas Research. There was a first phase last year dedicated to, let's say, a review of available literature on commercial offers, and then it moved on to a control release experiment. So deploying 17 different technologies on a facility where we control exactly the release. And the purpose is to see what are generally available in terms of performances from the different techniques, and can we have a harmonized approach for measurement within the EU? So also as a response to the European consultation for methane emissions. Oh. So the control release experiment was used a facility from that is located in Spain. It's a former compressor station. It's actually not operating at the moment. So on the site we identified there were several different release points. All the participants came on the site and made their measurement almost as they wanted. Of course, there were many constraints and many interplay between different techniques. So finally, there were 9 site-level technology and 3 bottom-up techniques. So going to release point one by one. Okay, so here you see also that several shape of release nodes were tested to represent a potentially different type of emissions, of leaks. One is a 25-meter high vent stack. It's what we call node 1. And then closer to the ground. Closer to the ground, you have a few different type of nodes. Actually, 4 different type of nodes: linear, circular, open-ended, etc. So the project was a collaboration between various entities, and actually, so the organization was made by Enagas. On the field, it was coordinated by Bureau Veritas, and us at LSCE, we helped with defining the release schedule, and we took the data independently. We were not measuring on the site ourselves. Okay. I'll put the microphone closer. Speak loud. Okay. Thank you. So you can see a few of the companies that you can see all the companies that participated here with their technology. So we had a cocktail of different technologies with in situ measurement from drone. We had 2 different types of lidars measuring methane. One that was helicopter borne, and one that was on a truck by NPL group. You had different type of infrared camera, handheld infrared cameras, as well as fixed infrared cameras. You had integrated path scan that were targeting reflectors on sending back signal into the system. And all these groups, independent, so came to the field, made their measurements, went back home, and they had a fixed deadline by which they should provide their best estimate of the emissions. And then we took that data and we compiled that for you. Well, actually, I can skip that maybe because. Well, it's giving just more information on the individual technique. I'm not sure I can go through this because it's quite small actually. So the result that we had in the end for the different techniques, we tried to look at the uncertainties that are reported by the groups. We have a different type of uncertainty reporting. And we estimate ourselves the uncertainty associated, or with NPL, the uncertainties associated to the control release experiment itself. For some releases, we had a significant uncertainty due to a mass flow controller that was not perfect. And so you can see that there is generally a fairly good agreement between each technique and the truth, let's say, from the release. Many, let's say, top-down techniques tend to overestimate the emission, while so it's from the top row and the 2 on the bottom left here are top-down. We call them top-down techniques. And here you have the handheld cameras and the high flow sampler, the handheld camera tend to generally underestimate the emissions. We have generally a fairly good correlation. So when let's say high releases are actually estimated to be high with various performances, what we see is that some techniques have a larger scatter than others. And this is when we take for each release the best estimate of each group. So we ask each group had 2 hours to make the measurement. And from these 2 hours, they should make the best use of it. Some groups had more constraints. For example, for the drones group, we try to have them doing separate type of let's say, work sequentially. So they had 20 minutes, and then the next group was coming in. So they had shorter time to make their measurement. That might be a part of the explanation maybe for the different performances. You can see the drone performances, they are here, and they tend to have a much more higher scatter compared to the other technique. You can see already from this data that there is some information that emerge also on the technologies that tend to perform well during all the different releases. You have the 2 LiDARs, they tend to have a quite good result, as well as the tracer release experiment. So the tracer release consists to release a known gas at a known rate close to the source. So what we can say already is that these different techniques, they are not the most easy ones to deploy, but they have quite good results. We try to synthesize this result to provide an overview of the different technique. So here, for each release, on each technique, we take the discrepancy, the difference between the estimation of the rate and the truth. And we calculate the absolute value of the relative error for all the releases for each technique. So ideally, all the techniques that are on the 0 line, all the measurements that are on the 0 line are the best ones. Each dot, so on the x-axis you have each technique. Each dot is one individual release. You can see the intensity, the leak emission rate here. It depends on the color of the dot. On the box on whisker plot for each technology are let's say the statistical distribution. So it's a median in the middle, and you have the first quartile on the second quartile here. So you can see the large spread of some technique, typically of the drone technique, and some of the fixed technique as well. You can see also in this figure, because we try to see another trade-off that we think is important, is to what extent each group able to provide information for a lot of releases? Because some groups may decide that the data is not good enough to provide as a result, and so let's say mention that this result is invalid. So we don't show invalid results, and here we count only the numbers of valid results provided by each group. So it's important because we made one assumption that proved not to be entirely true, but we made one assumption that when the group maybe when there are challenges with providing high-quality measurements, the group might decide to withdraw some result or to flag them as invalid. And actually, it is not true. There are several groups who manage to perform very well on many measurements, and some struggle for different reasons. It's not necessarily the quality of the measurement or the validity of the technique, but it might be really operational constraints. So one of the things that we found in the end is that, well, first of all, the positive thing is that almost everybody is always within one order of magnitude of the truth. So this is what it means here. We try to stick to the metrics of analysis of the paper by Ravi Kumar et al. In 2019 from the EDF challenge. And then we look at how many times is each technique within a factor 2 of the true value. And here we have a much more difference between the different techniques. You can see that the handheld OGI camera, they are typically how to say, handicapped by these metrics, because with the underestimation they tend to fall more easily outside of the specified range. And in the end, also, we try to look at how can we compare the uncertainties that we calculate from this study, so the relative error, the typical relative error of the technique, with the uncertainties that was provided by each group. Here, actually, so it's the two left columns. So here, actually, it's very challenging because there are very different ways to report uncertainty, expanded uncertainty, 1 sigma, 2 sigma. We try to harmonize this, but the work is not complete at the moment. So it's difficult to compare these two values, but what we see is that there is not a direct equivalence between the reported uncertainty or the assumed uncertainty for each technique and the performance that we find in the control release experiments. What that means is that it's really important to have to test the techniques, to go and make control release experiment and try to assess what is the actual performance of the technique and what are the actual constraints that you see on the field. Hop. Not working anymore. Okay. So in conclusion, so we had only 3 technologies that showed average error below 50%. The 2 LiDAR techniques on the tracer release. As I noted, these are techniques that require significant effort. The LiDARs, they need to be moving around, either with a heavy truck or a helicopter. They also need a lot of expertise around, of course. The tracer release requires that you put an acetylene bottle, or not necessarily acetylene, but in this case it was acetylene. You need to put it next to pre-identified leak point. It's complex operation. You can make it for, if the points are too close, it becomes very challenging to quantify separately the points. And then you need also a sensor that is able to measure both methane and acetylene, of course. We need further work to determine how this technology can be applied to reconcile bottom-up estimates. Here we try to compare these techniques, separate them as top-down or bottom-up, but we didn't go as far as recombining the bottom-up estimate with the top-down values. And what we see is that with bottom-up technique tending to underestimate emission, we see already the challenge coming at the very fine grain in our study. What we have also found is that this technique, we wonder how it will behave when you are in complex environment, like a LNG terminal or an industrial cluster with many different emitters. There we were in a perfect setting, close to the sea in Spain, with almost nothing in the area. It was a countryside, no other strong methane emissions. So it was quite easy to manage. We have not investigated the influence of other emissions nearby. There has been a follow-up study compared to that, measurement in Zelzat on a site in operation. So in this case, you don't have the truth, but you are in a real environment with a real constraint of operations. And that is the analysis is work in progress. And I think I finish here. And thank you.
Is it working now? Yes. So I will ask the 4 panelists now to come here to answer the potential questions. So Stefan, Jacob, and Nigel, please come to the stage. So is there any questions from the audience? So I see a hand raised there.
Yes, thank you. It was a question for Jacob on the flare efficiency study you did. So you referenced a lot of the data that Amy took. How did the data collected via the flypass differentiate between flare sources and sort of the other sources that Stefan alluded to, like your gas turbine exhaust emissions from direct drive compressors, from power gen, etc.?
Is this working? Yeah, is this working? Yeah. So other studies have visually confirmed flares. We were unable to do that from the aircraft. The only way that we seem able to do this is to look for concurrent peaks in our data of methane, ethane, carbon dioxide, and nitrogen oxides, and just look for where those line up, and I guess make the assumption that all of those components in the same peak is indicative of flaring. I don't know whether that's always going to be the case, but it's perhaps as good as we can do with the data.
Yeah, my thoughts was it might just allow for a wee bit of differentiation between the difference in the NOx concentrations in the UK and Norwegian sectors. In the Norwegian sector, your gas turbines are more likely to have DLE combustion on board because it's a newer technology essentially, and the rigs in the UK sector are quite old. Just might be an indicator of that. Worth knowing.
Yeah, I guess that can be the case. Yeah, it's the best we can do, I guess, with the data we've got.
No, that's fair enough. And to be honest, the fact it's sort of 98% anyway, sort of, is quite in line with what the industry is sort of.
Yeah, the numbers are coming out okay, so that gives us a bit of extra confidence.
Okay, so I'm Marie. There is a question from Trond here, in the first row. Eddie, sorry.
Thanks so much. Great presentations. I guess less of a question and just more of a comment to make a distinction in light of the presentations this morning on OGMP. That reconciliation here is being used to talk about bringing together different bits of data and from multiple measurements, which is fantastic and much needed, particularly as we assess the technologies, but pretty different than we use in the OGMP context when we talk about reconciling a bottom-up source-level measurement-based inventory with a site-level measurement. So, thanks.
Does this work? Yes, it does. So I have a question which actually is kind of free choice who wants to answer, but we have measurements with some tens of percents to several 100%, maybe even order of magnitude errors involved. Where does this go from here? How good can this become? Where do you see this ending up? Are we talking about sort of the single-digit percents of error in the end of emissions measurements, or what?
I can try. Okay, I can give a first answer from what we see. In the GERG study, there is clearly room for improvement. In this case, it was really, let's say, commercial condition. Groups were coming and followed their own protocol, and we didn't try to optimize anything, and we didn't encourage them to optimize anything. Actually, there are many, from my external view on the operation, there could be some improvement in the way you measure wind when you do mass balance. Where do you exactly measure wind? Do you measure wind following WMO standards? Do you have a wind LiDAR? So technically, on the technical level, you can improve a lot of things about the deployment, the choice of sensors. And in the end, we see that the techniques that manage to best, let's say, encompass comprehensively all the emissions, they manage to get the best results. So for the techniques that for whose it is most easy to capture all the emissions, they will probably get the best result. But that view is only, from this study, we only get a snapshot at one particular release because of the nature of the study. So it might be different with time variability.
Yeah, it's a great question, and I think we've been struggling with these uncertainties and biases for a while, and maybe we will struggle with these for a while going forward too. So I think what's important is to really characterize the uncertainties through studies like these. I think those controlled releases are really important. I believe Manfredi has already talked about or mentioned the controlled releases that through IMEO will start as well. Other groups have done them. So I think collectively these will characterize better what certain technologies can do. And then when it comes to reconciliation at whatever level, just different measurement techniques or like a level 4 and a level 5, I think this is where it's important to know these uncertainties, to understand, you know, how close, what can our target be of reconciling, right? And I think through all this work that we're doing, in the end, I think the uncertainties will come down. Like you just said, the technology providers that go through such a test release, they may have done it for the first time, and they're starting to learn not just to do the measurements, they know this already, but how to apply them really well. Under which conditions do you have to measure a certain way? I think this is a learning curve that has started a few years ago and will probably go on for a few years.
Thank you. Very nice questions. I have a similar question also to Daniel, but I will frame it a little bit linked to the previous question. I think when we have individual errors that are large, we can assume that if we sample a large enough population, that positive and negative errors, and they can come from intermittent or wind-related or whatever circumstance-related artifacts, they would cancel out in certain ways, right? Statistically, you could see maybe similar distributions. But if you have systematic overestimates or underestimates, then we run into problems. And I was really a little bit surprised also by these systematically higher drone estimates, where conceptually I think this is similar to what Anke has shown, a mass balance study with upwind and downwind comparison. And I always say you cannot hide anything in the atmosphere, so it should actually come up there. So it must then be related to some kind of the processing of the data that leads to these systematic effects, right?
Yeah, I fully agree with your point. So actually, initially in this study, we were excited to ask each participating group to provide us their individual pass for groups who do repeat pass measurements, and to see how much do you really increase the performance by square root of n as you accumulate more data. Actually, in the end, we collapsed a little bit under the heterogeneity of the data set that we collected from the different groups. So we acknowledge this problem, and we also realize that, as I said before, some groups had 2 hours of measurement, some groups at 20 minutes for operational reasons. And is it fair? Is it not fair? It's difficult to say. And I assume that you will improve a lot the uncertainty if you manage to accumulate more measurement, but not all techniques are equally free of bias.
Yeah, that was actually my original question. How often have the drones, of course, they need some time to measure. We saw it also in the other presentation. And in a 2-hour window, and when you have to set out things, maybe you are limited also by the number of transects that you can make in a certain area.
Thank you. Sorry. There's a question for Stefan in this case. You brought up a slide that showed the split of fuel gas between the Alpha and Bravo compressor trains on the Cygnus platform. How much of a role did that play in the interpretation of the data? I was just thinking on a practical level, a lot of our rigs won't have that level of metering. Cygnus is quite new.
Yeah, we have started looking into this. We're not finished yet. What we were surprised at was that there was relatively, like, even just by the methane concentration signal itself, there was very little coming out of those compressors. What we have to look more into is what were the operating states at the time when the rotor drone measured. So right now we're looking into combustion efficiencies of 99.9999%, something in that order, which was fairly surprising. But it also looks like we were missing something. And so is that because on other days perhaps the turbine was working under a different load? Could have caused a problem.
I mean, so just from my own background, I would imagine you probably see more methane from the power generation exhaust because the amount of spin in reserve they use offshore to ensure security of supply means those turbines are historically loaded a lot lower. Compressor turbines tend to be loaded quite high, even in low gas rates, because they recycle the gas to avoid damaging the compressor. So combustion efficiency generally will be a lot higher in a direct drive GT compared to power generation, if that's any help at all. Thank you very much. That's useful to answer my question. Thank you.
Okay. Are there any additional questions? If not, so we will go now for the lunch break. No? Go for lunch. No, no. I wanted to ask for a huge applause for great panelists. And now, yes, lunch break.